everyone's doing well. First thing I want to tell everyone, first thing I want to make you all aware of, I made an announcement last weekend, was it? Essentially, I realized some of you were missing homeworks. And as I had mentioned before, the homeworks are the easiest grade you can get in this class. And they're worth just as much as everything else is. So I decided to allow you guys to submit late homeworks. Now, here's the way that this is going to work. All homeworks, starting from homework one, all of them, essentially, I will allow you to submit late assignments until May 8th at 11:59 p.m. That's, oh, just 2 weeks from now. But yes, you have 2 weeks.
Thank you very
Between here,
much, Professor.
you're welcome. Between here and May 8th, you may also submit the late homeworks. However, know that because they're submitted late, at most, um, you'll get a grade of 70%. Um, but it'll should keep you guys from failing. After May 8th at 11:59 p.m., I will not accept any late homework assignments for any circumstance. Understand that this is a courtesy I'm extending to you guys, so please work with me. After May 8th at 11:59, I'm just going to repeat it. I will not accept any late assignments. This is only for the homeworks. I will not be offering makeup quizzes or exams. Well, everyone was here for the exam, but I won't be offering any makeup quizzes. For the homeworks, you guys already know the deal. As long as you do the whole assignment, as long as you answer every question in the homework, you will get full points, which in this case is up to 70%. Again, that limit is being placed because it is late. One thing though, if you submitted a homework assignment, you got a grade for it already, I'm not accepting these submissions, though I think there hasn't been many of them that submitted a homework and didn't get a full grade. But know that if you submitted a homework and you got like a 60, for example, and you resubmit, I'm not gonna change it. It's only for those of you guys that missed the homework assignments. By the way, Collins, I got the quiz. We're good. All right. You don't need to worry. Um, but yeah, it'll be for everyone. Just make sure. Again, gotta submit any late homeworks. I know this is like the third or fourth time I say it. Just make sure you get it in by May 8th at 11:59 p.m. Any questions, comments, concerns about that? Anything I just said up to this point? All right. If there are no questions, then let's actually begin with today's lecture. So today's lecture, it's not gonna be as bad as some of the recent ones that we've had. Um, it is still critical though, and today's lecture, the way that I see it, it's somewhat of a payoff for everything you've learned and everything you've done up to this point. Um, but before we get to that, let's do the quiz. Oh, let's begin with the quiz. So, question one of the quiz gave you the transfer function g of s is equal to s plus 3. Now, as usual, if you did the homework, both problems on the quiz should have been familiar because I took both of them straight from the homework. So the first step is going to be we'll replace s with j omega. That'll give us g of j omega is equal to j omega plus 3. Right away, we can tell our break frequency for our Bode plot is omega b is equal to 3. All right. Now, again, because of the nature of Bode plots and how they operate, we're not going to be able to sketch something 100% accurate by hand unless we sit here and calculate the location of every single point for our magnitude and our phase. So instead, we will create asymptotic approximations. For our magnitude at low frequency, we can say the following. So g of j omega, right? What's going to happen to it as omega is effectively 0? G of j omega will become 3 or almost 3. Now, when we convert to decibels, this gives us 20 log base 10 of 3. Now, what this tells us is that it's a flat line for when omega is between 0 to when it's less than the break frequency. Okay? That's what this is telling you. Between 0 to the break frequency, we're going to have a straight line right here at 20 log of 3. Now, on the other hand, at high frequencies, g of j omega, right, it will effectively just become equal to omega. This is when omega becomes very large. All right. So because of that, this will become 20 log of omega, which because omega is our the independent variable, it's just rising. You can think of it as our time, it's our frequency. It's just gonna keep growing, right? So in other words, we can tell that we're gonna be growing at a rate of 20 decibels per decade. Now our phase angle, just because of the fact that this is only a 0, this is gonna be growing at 45 degrees per decade. However, there are some caveats to this, as we saw in our previous lecture. We're going to start from 0.1 or 1 decade before omega b. So that'll just be 0.3 in this case. And from there is where we start growing at a rate of 45 degrees per decade. Then we'll hit 45 degrees when omega is equal to 3. And by the way, if I said that we start from a break frequency of 0.3, I mean we start from a frequency of 0.3. In other words, when our x-axis is 0.3, is when we start rising. And then we'll hit 90 degrees. One decade after our break frequency. So that'll be just 10 times our break frequency, which is 30. So even though this is relatively simple, from this we need to draw an approximation of our Bode plot. So what we can say here, we have 20 log of 3 here. We'll put 3 over here. So what we know our plot is going to do for our magnitude is we're going to start at a constant value of 20 log of 3. And then when we hit our break frequency, we're going to start rising. And we'll keep rising at a rate of plus 20 decibels per decade. And that's your magnitude plot. Now for the phase plot, as we just described it, has a little bit more details to it, but nothing new crazy. We have 0 degrees here, we'll have 45 degrees here, and we'll have 90 degrees here. So we'll put 0.3 right here, we'll put 3 right here, and we'll put 30 right there. So just to make things a little easier, we know at 45 degrees, we'll hit that when omega is equal to 3. And then when omega is equal to 30, we know that's when we hit 90 degrees. We start rising when omega, or our frequency, is equal to 0.3. So before then, we're at 0, we're a flat line. When we hit 0.3, we start going up by 45 degrees per decade, passing or hitting 45 degrees when omega is equal to 3, hitting 90 degrees when omega is equal to 30. However, we do not grow past 90 degrees. We stay constant. All right. But again, this is 45 degrees per decade. That's the slope at which we are growing. Is there any questions, comments, concerns, doubts, any confusion about anything I've done or anything I've said up to this point?
I have a question.
Yes.
So for what would it be? Just in this case, the graph for magnitude and pole, it would always be plus 20 decibels per decade and plus 45 degrees per
Yes.
decade. Okay.
So whenever we have a 0, right? In this case is s plus 3, we have a 0 and -3, right? Whenever we have that, we can say that this will incur a plus 20 decibel growth on our magnitude after we hit the dedicated break frequency for that 0. And it's going to have a plus 45 degrees per decade growth on the phase plot. Now, the reason why it matters to remember this is because, as you saw for the last example we did in class, and also for the last homework problem, if you have multiple equations, all you have to do is just take these rules that we went over and combine them, keeping in mind for which values of omega, for which frequencies they're valid for. That's why we sit here and we find out, okay, we're gonna start growing when omega is 0.3. So between a frequency of 0 to 0.3, we're gonna be at 0 degrees when we're gonna grow. And once we hit 30, we're gonna stop growing as well, right? We're not growing at either of these points. Now, in this case, since this is all we have, it doesn't matter. But if we had multiple things, let's say we had something with 1 0 and 1 pole, right? All of a sudden, we would just draw them or think of them individually and combine them. Where just because right here we have plus 0 degrees, doesn't mean that our 0 would also incur, sorry, our pole would also incur plus 0 degrees in this specific region. Does that make sense?
Yeah, I got it.
Okay. So for the second problem, I'll go ahead and I'll do it just like I did this one, but I can just tell you guys, it's the same exact thing as this, just kind of mirrored, right? Key aspect, the key thing you have to remember is whenever you work in decibels, multiplication becomes addition, division becomes subtraction. Wholes are in your denominator, they're being divided, right? So effectively, when you have a pole, it's the same as doing subtraction on a logarithmic scale. All right, so that's why, and you'll see this in a minute, but here we're growing. When we work with our pole, we're going to be decaying. It'll be at the same exact rate, but it'll be decaying instead. So the graphs will effectively be mirror images of each other. So the second problem, as I just said, have our system g of s equal to 1 over s plus 3. So we have a single zero, sorry, we have a single pole, no zeros. I misspoke. This is going to become what? Oh, that's why. So this is going to become g of j omega, or we just replace s with j omega. So it'll be 1 over j omega plus 3. So right away, we can see break frequency again. In this case, it's going to be at omega b is equal to 3 again. Now, at low frequencies for our magnitude plot, which is again when omega goes to 0. And when I say omega goes to 0, I mean omega right here. Right? So if that becomes 0, all we'll be left with is g of j omega is equal to 1 over 3, or well, approximately equal to 1 over 3. Right? In decibels, this is just minus 20 log of 1 over 3. Where again, it's minus 20 log, right? That negative stems from the fact that we have a pole. We're dividing. We're in the denominator here. I'll reiterate again. In a logarithmic scale, multiplication becomes addition. Subdivision becomes subtraction. All right? So because this is in the denominator, it becomes subtraction. It gets that negative sign. That's where the negative sign comes from right there. All right? Now, on the other hand, at high frequencies, we're going to get g of j omega approximately just being equal to 1 over omega. Now, in decibels, this is going to give us negative 20 log of 1 over omega. All right, any questions up to this point? Now, yes?
Can you explain the logarithmic thing where the sign changes?
Yeah, so whenever we deal with a logarithmic scale, and think back to instrumentation and data analysis, I think that's 3615, or it might be 3625, most likely 15. But when you took that class, you should have done a lot of frequency response, plotting a lot of things on logarithmic paper. The reason why I'm bringing that up is because when you're dealing with a logarithmic scale, anything being multiplied becomes addition. Anything being subtracted becomes division. So, sorry, anything being divided becomes subtraction, it's the other way around. Let me just show you guys real quick from our previous lecture. We have right here. So, Derek, since you're asking, notice this transfer function. We have in our numerator, k times j omega plus a times j omega plus b. Those are our zeros. Those are our roots in the numerator. In the denominator, we have j omega times j omega plus c times j omega plus d. Okay? Now, if we were to convert this to decibels, it would just be 20 log of k, which was in the numerator, so because it's in the numerator, it's positive, it's added, plus 20 log of j omega plus a, which as you see is in the numerator, so it gets added, plus 20 log of j omega plus b. Again, numerator, it's going to get added, right? And then everything in the numerator, j omega plus c, and j omega plus b, those are all going to be subtracted. So we have minus 20 log of j omega, minus 20 log of j omega plus c, minus 20 log of j omega plus b. So effectively, that's what I'm trying to remind you guys of from my most recent lecture. Does that make it a little clearer?
Yes.
Going back to this, as I just explained, we'll have a negative sign. So in this case, we'll have minus 45 degrees per decade as our slope. But again, we start at 0.1 times our break frequency, which is just going to be 0.3. We'll hit 45 degrees when our frequency hits our break frequency, which is 3. And we'll hit 90 degrees when we're 1 decade after our break frequency, or 10 times 90, which is just 30 again. So we take all of that, and we can once again make our asymptotic approximation of our Bode plot. So it's going to look like will be, now there's different ways to label your graphs and make the axis for your graphs. Like some of them will use a single x-axis for both magnitude and phase. And you can totally do that. I think our book has that a few times. But as I said, this is my best case. As I said right here, we'll be flat at negative 20 of log of 1 over 3. Then we'll have a break frequency right here of 3. So when we actually sit here and plot our magnitude, we'll be flat at negative 20 log of 1 over 3 until we hit our break frequency, in which case we will keep on decreasing at a rate of minus 20 decibels per decade. All right, any questions of why it looks like that, why I came about that plot? Any doubts? Anyone not understand anything whatsoever up to this point? So, moving on to our plot, for which I did not leave a space, lovely. Right here, we'll be at 0 degrees. Oh, hold on. I made one small mistake right here when talking about phase angles. We'll hit negative 45 degrees when omega is equal to 3, when it's equal to our break frequency. And we'll hit negative 90 degrees when omega is equal to 10 times our break frequency. Just wanted to clarify that. So we'll have negative 45 degrees here, here, 0.3 here, we'll have here, and we'll have 30 here. So again, we know from 0 to 0.3 will be flat. Then once we hit point 0.3 will start decreasing at a constant slope of minus 45 degrees per decade. When we hit 3, when we hit a frequency of 3, which is our break frequency, we'll hit negative 45 degrees. When we hit 10 times our break frequency, which is 30, we'll hit negative 90 degrees. And once we hit 90, we stay flat at negative 90. Okay? I've gone about that a little fast, but I feel like you guys understand it well. If not, please let me know. Anyways, any questions, comments, concerns, doubts? Anyone not understand anything I've said up to this point? Now, do expect a problem like this one to show up on your uh, final. I won't make it something as crazy as the final problem of the homework, but that's not really that big. What I might do would be combining or giving a problem that has one pole and one zero. All right, so just understand how they work, keep them in mind. If you don't, come to office hours. But I'll reiterate again. Does anyone have any questions about anything I've said up to this point? No? Okay. So if that's the case, then let's begin with today's lecture. So let me give some nice poetry to you guys, right? As control engineers, what would you say your job is? Right? You guys have seen enough of this and done enough of this that I think you should have an idea of what the job of a control engineer is. So tell me, what is the job of a control engineer?
Designing tune controls algorithms.
Well, it doesn't have to be an algorithm. The word ideally should be systems, but yeah, control engineers design controls for systems. That's true. However, actually, before I say this, anyone want to take another crack at it or no?
I was gonna say they maintain automated systems.
Maintain, yeah. Now, okay, I'm gonna go on a bit of a rant. The job title control engineer has kind of lost its sense. It's kind of lost its purpose because there's people that get the title, and what they do isn't control engineering. They do applications of control engineering. They apply them. They don't build them. They don't design them. They're not thinking actively so much about the things that we go here. Some of the concept they might think of them slightly, but they're not going through a root locus plot. They're not caring about the voting plot. They won't actually design the controller itself. All they're doing is just applying. And there's a lot of people that have the title nowadays that aren't actually designing. So the answer someone just gave of maintaining control systems, that is technically correct. But ideally, or in the old term of the word, it wouldn't fully fit the bill. Yeah, you could have the person that designs and maintain them, but generally, your job is to design, or ideally, your job should be to design. A controller such that your error, which again is your input minus your actual output, goes to zero over time. Yes. So the whole purpose of what you guys have been doing is so that our error it goes down with time, right? So if we have a large error, our goal is to get it as close to, or if not at zero, as time goes by. We want to get rid of any errors in our control structure. We want to make sure that the only thing that gets through to our plant and the only thing that our plant does is match our input, match our desired result, match our set point. All right. Any questions up to this point? Any doubts? Now, one way to implement this, or one of the most important structures in control systems, is called a PID controller. Don't call it a PID. Please don't. If you have an interview, you call it a PID, people will look at you weird. I pinky promise they will. Say the letters, that's just three of them. PID controller. Why do we say the letters individually? Because they each stand for something. It stands for proportional plus integral plus derivative. All right. Now, what does this mean? Essentially, we're going to take our error and we're going to apply a proportional amount to it. We're going to integrate it and we're going to derive it. And you guys by hand will be doing these things, so don't worry, because I know you all forgot math at this point. It's okay. But that's what the controller is actively doing. All right. Now, why do you care about this? Why is this so useful? You'll see later on throughout the class, but essentially, this is a controller that's relatively easy to design. It is generally not that expensive, or comparatively not as expensive to implement, and it works rather well. Okay. Now, one thing to know is the fact that you won't always need all three. So, for example, and you'll see this in an example later today, and you'll see this in your homework. It might not be a PID controller. It might be a PI controller, or it might be a PD controller. All right. It might just be a P or an I controller. Right. You can have some or one of some of these at a time, and it'll still work. The only one you can't have by itself is derivative. Anyone tell me why?
Because if the derivative, if I'm not mistaken, the derivative is the space, the area under the curve. So that has something to do with. No, I don't know. Actually, never mind.
So the integral is the area under the curve. Your derivative is your rate of change. It's your slope. But here's the thing. If you take the derivative of a number, what do you get? This one you guys have to remember, even if you don't remember math. What's the derivative of a number?
One.
No. The derivative of any number is zero. The derivative of x, or the derivative of just a variable, would be one. The derivative of any number would just be zero. So if all we have is derivative, and all we take is the derivative, then it'll be nothing. It'll just be a straight line, right? We'll touch upon this later, but I just want you guys to start thinking for yourselves, actively trying to understand what I'm putting down. So why these three? What do they let us choose? Why are these three so special, right? That's because they correspond to something. So the proportional value essentially lets you see the present. Your integral value will let you see the past. And your derivative, well, there's only one option remaining, is the future. Now, it doesn't quite let you see the future, obviously, but rather it lets you see your future trend, most likely where you're going to go in the future based upon what happened in the past, which is, in other words, just your slope, right? Mathematically, things tend to follow a pattern. So if we can figure out the slope, if we can figure out the rate of change of something, then we can actually predict where to go in the future. All right. Any questions up to this point? I know it's still a little abstract, but any questions?
Um, Present, past, and future.
Yes.
So how does each component represent the ghosts of Christmas, present, past, and future?
Oh,
I'm sorry, Collins. I'm confused at your question.
How does each one represent present, past? How does each component represent the present, past, and future?
Well,
Or
the proportional represents the present, the integral represents the past, and the derivative represents the future. When we say proportional, all we're saying is just taking whatever the error is right now and multiplying it. I'll show this deeper in detail in a bit,
Professor.
right? So just, yes.
Sorry, I didn't mean to cut you off. I thought you were not. My bad.
Oh, no, all good. So the proportional value is just our error right now, scaled by a value. The integral, right? When we take the integral of something, what are we seeing, right? We're seeing the summation, we're seeing the history of everything. Because remember, if we have a graph, right, what the integral is going to give us as we move on is going to be this area. But if we make it a number, that number is the summation, right, the total of everything we've seen up to this point. So the integral is looking at what we have not only right now, it's also letting us see the past, what happened. Whereas the future, what the future represents, or the derivative tells you your rate of change, right? So let's say we have a slightly different graph. Let's say we have a graph that looks like this, right? From here to here, we can say that our derivative, our rate of change, is effectively, we're not changing. We're not going up, we're not going down. It's a straight line. So our change in error is small. Okay, we can't really tell how it's going to go in the future. However, right here, we have a large change in error. We have a slope. So therefore, we're able to predict, if we're right here, right, as we go decreasing, we can more or less predict what will be at this time right here. Does that make more sense mathematically? Again, I'll get slightly deeper into these. But Collins, does that give you a better idea?
yeah, so derivative represents future because of rate of change. Cre-
Yes.
Okay.
So let me show you something. In terms
Right,
of a system,
because derivatives are slopes.
that's so let me show you guys something. Let's say we have our system block diagram that looks like this. The first thing we're going to feed into is going to be our PID controller. Our controller is going to feed into the plants itself. Now, plants is a term I've used before. Does anyone remember what it is? No? All right, your plants, and write this down if you don't remember because I'll be using it a lot. Your plant is your system. It's what you're trying to control. let's say that the system at hand is a car, right? We're writing a controller for designing a controller for what's it called? The cruise control of a car. In this scenario, the plant would be the car. That's the system we're controlling. If we're designing a controller for the position of a servo motor, the plant is the servo motor itself. It's the system, the dumb part that can't think for itself, that we're giving thought to, that we're allowing to refine the output of. It's the goal that we want to manipulate. That's what our plants is. All right. Now, what we're going to focus on, PID controller, here is what's inside. All right. Coming in, we'll have our error. All right. That's our input to the system. And it's going to split into 3 branches. First branch will be KP, our proportional. Middle branch or second branch will be KI times 1 over S, which is our integral path. And our third branch will be KD times S.
Good.
Now, all 3 of these will be added. And this is going to be the output of your PID controller. All right, so let's get a little deeper. First, this top branch up here, right? This whole top branch, it corresponds to our proportional. So it is referred to as our proportional path. Our second branch, it corresponds to our middle branch right here. It corresponds to the integral. So we can call this our integral path. Our bottom branch here corresponds to our derivative. So we can call this our derivative path. All right, so let me get a little deeper into what I was talking about earlier. All right, so proportional. Path. What is it? As I mentioned before, the output of the proportional path is your error scaled by AP. Now, before that, actually, let me just point something out. We have 3 gains, right? Each path is controlled by its own gain. Now, because of that idea, remember how I told you you don't always need to have all of them? If we set one of the gains to 0, all of a sudden that path doesn't exist anymore, right? We won't see it present in the output of our PID controller. So KP is our proportional gain. KI is our integral gain. And you can guess what KD is, not the basketball player. It is our derivative game. So notice how each of them is being scaled. By the way, from this block diagram, you should be able to notice the integral path, Ki, is being multiplied by 1 over s. The derivative path, Kd, is being multiplied by s. Can anyone tell me why? It is something we have seen before in this class.
Is that the feedback?
No, not quite. There's no feedback present inside of the PID controller. On the whole system, yes, but inside the PID controller itself, no.
I know what it is, but I can't quite put my finger on it.
The transfer function?
Oh, that's
Getting closer. So, remember when we had a differential equation, right? I gave it to you in the time domain, and it was being taken as a derivative, right? If we have, let's say, for example, d of ct over dt, right? What is the Laplace transform of this? This is something you guys have all done before.
E.
It's s times dr or d of s, right? Because we're taking the first derivative, we have s, yes? Can you guys remember that now?
Yeah.
Okay. So now does it make sense where this s right here in the derivative path comes from?
Yeah. And then the next one would be the integral, so you'd have to
The
use.
integral. The integral is what? Integration is the opposite operation to derivation, right? So then it makes sense that we'll have the opposite operation to what we have down here. This is being multiplied, so we'll just take the reciprocal of it and have it being divided. So that's why the integral path is being multiplied by 1 over s. Now at the same time, the proportional path, we said is just a number. So it has no s term in it. Make sense to everyone?
Yeah.
All right. So, as I was saying earlier, our proportional path, the output of our proportional path is the error at that moment, all right? Scaled by Kp. What does it mean when we scale something? We multiply it. Everyone's here is hopefully able to do that, right? So, in other words, when the error is positive, right, the output of the proportional path is also going to be positive. When it's 0, output is 0. When the error is negative, the output is also negative. All right. So if we plot our error, right, and we make it look something like this. Right, so let's say that our error looks something like this. Our proportional is essentially just scale with that. So again, if it's positive, our proportional is going to be positive multiplied by whatever our proportional gain is. Let's say our proportion, let's say this value here is 10 and we have a KP of 5. The output of that's going to be 50. All right. On the other hand, once we hit 0, 0 times anything is 0. And then once we hit a negative value, we'll have a negative will have a negative proportional output. Right? I hope you guys are able to follow why the proportional is giving us the present, because it's at that instance where you're at right now. As your error changes, your proportional changes along with it. Now, on the other hand, as your error moves over time, your integral path sums it all up. And it scales it by your integral gain. When we plot this, add some more details, so I'll touch on those things. When we plot this, as we saw before, right, this is just going to be the area. It's not only the area, it's the summation of the area under your curve. All right. Now, here starting out, you can see that your integral path output is going to be positive as you go summing the area under the curve that's positive. But then as you start having an area under the curve that's negative, you're going to go decreasing. Okay. Now your derivative path is just the rate of change of your error scaled by your derivative, AB. Now, just from hearing that, we can surmise the following. A slow change in error results in a small output in your derivative path, right? Whereas on the other hand, a fast change in error results in a large derivative path. Output. So again, I'm just kind of reiterating at this point, but graphically what this is going to look like, this is going to be the rate of change. So up here, or let me use it up here, our change in error is small, right? Because there's very small, almost no change in error. Whereas on the other hand, right here, our change in error is large. So this will give us a large output on our derivative path. Any questions, comments, concerns, confusions, doubt up to this point? All right. So far, I hope you guys realize that a chunk of this is just conceptual. So far, we haven't really gotten into any math. So again, I'm just going to keep explaining in different words, right? For proportion, it's your error right now at that single instant. So we can have our output in the time domain as Kp times EFT. Now, bigger error will result in bigger correction. Now, put that in quotes because you see that it's not always desirable to have such a large sweep. Now, on the other hand, your integral is your accumulating error over time. In other words, past. Right? Now your output for this is just the integral, or before that, your integral being multiplied by the integral of ET derivative of time. Now, something key about the integral, or the reason why you would even use it in the first place, is to reduce your steady state error. In other words, it lets you reduce a constant error. All right. On the other hand, your derivative is how fast your error is changing. Now, we'll say future just to make it look a little more uniform and a little nicer. But again, you're not quite looking at the future. No one can tell you, nothing can tell you exactly what the future is. But what we're actually seeing is just a trend or a future trend. Understand the difference between future and future trend is slim, but there is a difference. Future is exactly what's going to happen in the future, whereas future trend is more of an educated guess based upon what's happening. So that's what the derivative is able to get us. Now the output in the time domain is just going to be your derivative gain times just the derivative of E of t with respect to time. Now, this matters because it is going to reduce your percentage overshoot and it increases your damping. Okay? Questions, comments, concerns, doubt of anything I've said up to this point?
No, not so far.
Now, in the time domain, the output of a PID controller is just the addition of these three terms I outlined above for you guys. So for proportional, we have Kp, our proportional gain, times E of t, plus our integral gain, which is, or our integral path, which is our integral gain, times the derivative of E of t with respect to time, plus our derivative path, which is the derivative gain, Kd, times the derivative of E of t with respect to time. All right, all I did was put these three together and remind you guys of the fact that they get added together, okay? Your PID controller, when you use all three, it's outputting the sum of all three paths. So let's go over a quick little concept, right? Let's go back to our old friend, an HVAC system, which, as a reminder, an HVAC system stands for heating, ventilation, and air conditioning. This is a very common application of controls, though most of the time when you get a job in this field, it'll be applications of control, not the sign. Um, but how do each of these three paths actually matter? What do they do to an HVAC system, right? So P, our proportional path, it is going to react to the current temperature error. All right. Our integral in a HVAC system, it is going to remove any constant error, anything that is constantly being seen. Now, one example of this would be what? An open window. Right? Open window could be letting hot air out, hot air out or cold air in, right? So that's a constant error in your system. By having the integral, it is allowing you to compensate for that constant error. So you're able to remove that constant error from your output response. Now your derivative in this scenario, it is going to smooth out fast temperature changes. Helping you avoid your percentage overshoot, or just avoid overshoot, which in this case are temperature swings. Now, why does the derivative matter? That one seems to be the impactful out of these three right here. Well, your derivative type is going to matter because let's say someone opens the door real quick and there's a blizzard going on outside and they let a bunch of cold air into the house that's warm. Now, at that single instant, you're going to feel a ton of cold, right? So your proportional is going to say, hey, there's like a very, very high error margin right here. Wrap this up. However, your derivative is going to compensate for that and say, hey, slow down. There's not really any way to change, right? Because the door only got open for a little bit and only a little bit of air was actually let in, we're not going to shoot all the way up and start blasting the heat at 100%, right? The door's only open for a moment. I hope that makes sense. I hope this is starting to give you guys a better idea, a better grasp on how the PID controllers work. Any questions to this point? We're going over more examples, but I just want to see if and there's anything you guys didn't understand up to this point. All right. Some of you may be thinking there's no map so far. Don't worry, we'll get to it. Not quite yet, but we'll get to it. You're not safe. All right, so let's go over another example. One example that I mentioned a second ago was cruise control. Now, if you don't know, cruise control in a car lets you set a constant speed for your car to be at without you constantly having to worry about mashing the throttle or changing your angle of acceleration, essentially. Now, the reason why you would care about that is if you're going on a long road trip and you're just on the highway for a few hours, it's your leg's gonna get tired, right? Small comfort, but trust me, you do notice it. Now, the way cruise control works is that it's gonna keep our car at a constant speed. So let's say we want to keep our car at a constant speed of 60 miles per hour. Tragically, we're limited on average to more or less that speed throughout the country. Germany has a great take on this, where they have autobahns. Those are highways without speed limits, and they work wonderfully. We're not in Germany. So let's say we want to keep our car at 60 miles per hour.
Actually, I've actually been to Germany.
I hope it was nice.
Yeah, it was. Yeah, I've seen the Autobahns.
I'm glad you have. So let's say our
Enough.
desired speed is 60 miles per hour, but current speed is 50 miles per hour, right? Our error E is going to be equal to the 60 minus 50, which will just give you 10 miles per hour. That's the difference between where we're at versus where we want to be. So, in terms of a block diagram, right? Our input is going to be our set speed of 60 miles per hour. That's going to feed into our adder. And our adder is going to feed our error, E, to the PID controller, the output of which controls your car, which is your plant. Remember, the thing you're trying to control is your plant. And then our output is going to be our actual speed. Feedback path right here. So again, in terms of what each of the three paths are going to do, your proportional path, right? It is going to give immediate throttle response or increase in throttle. Proportional to your error, right? Then your integral, it is going to keep adding corrections if your speed is less than 60 miles per hour. And in this case, your derivative path is going to reduce aggressive acceleration. Essentially, it'll keep you from feeling like you're flooring your car to hit your set speed, all right? Now, the reason why you want to do that is because it's going to remove any jitters present in the movement of your plan, the movement of our car, which if your car keeps jittering as it's moving straight, you're going to get motion sickness. You're going to hate that, right? So we don't want that. So in terms of our output, how it's going to look, right? We'll have our set point right here. That'll be 60. And we'll have our starting point, our actual speed right here of 50. So I want everyone here to follow. Remember, we turn on our proportional, or the proportional path turns on, right? And it's going to say, hey, there's a big difference, give a big input. So it's going to give a big constant input, and it's going to push us to a big value. But then all of a sudden, our error is no longer positive, it becomes negative. So we start to slow down. But then because we slow down, we actually drop below where we want it to be. So then this is where our integral kicks in. And that little amount that remains it is going to allow us to actually compensate for it and go back to our set point. And the whole time, what the derivative is doing is keeping us from doing this to our acceleration, right? From moving the car up and down, up and well, not moving the car up and down, but from accelerating and braking many hundreds of times each second, right? That will not feel good. The derivative is smoothing that out. Now, any questions, comments, concerns, doubts, confusion about this example I just explained? All right. Don't worry, guys. I know you're all worried because you haven't seen the fun part. You haven't seen the math things. All right. I know you're all worried. It's okay. We'll get to it. So, again, just to keep reiterating, and this is the last one before we get to the fun part. We'll have a value here. We'll have our purpose. And we'll have our impact of what too much of each value can do. Right? So, proportional integral derivative. The purpose of our proportional path, right, is going to give a fast response. It's going to give a quick correction, right? Why? Because it immediately reacts to the error. However, on the other hand, as you saw right here, what problem did that cause? We had an overshoot, right? And then that overshoot essentially resulted in oscillations. So too much of it can result in overshoots and oscillations, right? Now for our integral path, what's it going to do for us? It is going to remove steady state error, which again, we can define as just a constant error. However, the downside to having too much of our integral path is that it can give you a slow response or a larger percentage overshoot. Now your derivative path, on the other hand, it is going to improve damping, and as a result, it also reduces your percentage overshoot. However, it is going to result in increased sensitivity to interference. Because here's the thing that I haven't mentioned so far about the derivative path. The derivative path, it's looking at the whole rate of change. However, if we have an interference sneaking into that rate of change, right? The bigger the gain for the derivative path is, the more sensitive, the more impactful each interference becomes. All right. Now, from this chart, there's one thing I want you guys to realize. All three of them balance each other. What having too much of one does as a positive, the other has as a negative. So one can fix what the other does. However, don't just think, hey, I'm going to set them all to the same value and that'll work great since they all offshoot each other. No. You need to actually worry and care about the values of each of them because your system's not going to need the same for each of them. Each of these three will be as impactful depending on the system, right? Before we move on to the great part of today's lecture, to the fun part of the lecture, Are there any questions or comments or confusion? If not, then let's actually get to the fun part, the math. So there's a lot of ways you can honestly apply math to your PID controllers. And given what you guys have gone through in this class, I decided to just approach this from the simplest angle. All right, I'll give you guys some examples, but they won't be extremely large. But you still get something out of them. Now, what we're going to be doing is assign a PID controller that yields closed loop poles at s is equal to -2, -3, and -4. Now, you'll see this in a bit, but realize what I'm telling you. I'm telling you that our PID controller is letting us control the location of our poles. Why does the location of our poles matter? Can someone tell me, please?
Can you repeat that again, Professor?
Why does the location of our poles matter? What does the location of our poles tell us? It's been, I think, 2 lectures since we went over that. So let's reset. What does having poles on the right-hand plane tell us?
The system is unstable.
Good. Yes, that's correct. Thank you. However, I'm telling you that by manipulating a PID controller, we can control the location of the poles. We can decide where our poles go. All of a sudden, we can actually use a PID controller to let us make an unstable system stable. Are you guys starting to see and understand the power of a PID controller, why it's so commonly used? So this is actually going to be relatively simple. This is why I'm saying that I'm giving you guys a break with the way I'm going to have you guys work with this semester. So we'll have our block diagram, we have our input, we have our adder, right here. We have our error going into our PID controller, and we have that going to our plants. Here we'll just have our output, and here we'll have our feedback path. Now, our plant, right? Just the plant by itself, it's going to have the following transfer function: 1 over s squared. Okay? Now, again, so far, I think there's nothing new to what I'm saying. Now, the transfer function, and the notation might get a little confusing, but I'm going to call it g of PIDs. So in other words, the transfer function of our PID controller. This is going to be Kp plus Ki over S plus Kd times S. All right, just the summation of the three. Now, just to make this easier to work with, you can't keep it the same and solve it. This is going to take more steps. But just to make it easier to work with, what we're going to do is we're going to multiply the whole thing by, what do we multiply by? We're going to multiply these two. We're going to multiply Kb and Kp by S over S. Why? To have them all have the same denominator. So bear with me, and I'm going to rearrange. Notice that now the derivative came first. is going to give us kd squared plus kp times s plus ki. However, they're all going to have the same denominator of s. As a reminder, what we just did is we multiplied kd and kp by s over s, which is equal to 1. However, it allows us to have a common denominator amongst all three terms. All right, so that's the feedback of our PID controller. Not the feedback, the transfer function of our PID controller. Now the forward path of, or in other words, our open loop transfer function, our OLTF, is just GPID of S times G of S. Or in other words, this is going to be KB S squared plus KP times S plus KI all over S times 1 over S squared. This would just give us KD S squared plus KP times S plus KI all over S to the power of 3. Now, we're almost there, don't worry. Up next is going to be our closed loop transfer function. In other words, the transfer function of the whole system. What we did just now, our open loop transfer function, is just this. All right. So then we're reducing those two blocks to just a single block effectively. And then the next step is to take the transfer function of the whole system, our closed loop transfer function, which is going to be T of S equal to GPID of S times G of S. In other words, transfer function of our PID controller times the transfer function of our plant over 1 plus GPID of S times G of S. Now what that is going to give you, I'm not going to go through the steps of working it out here. I know you guys are, well, you guys should be able to work it out at this point, but this is going to give you KD S squared plus KP S plus KI, that stays the same, divided by S cubed plus KD S squared plus KPS plus KI. Now, this right here in the denominator, that is our characteristic equation. Or when you set it to 0, it's the characteristic equation. Technically. Just by looking at this as a characteristic polynomial. You get the gist of it. Why it matters is because it tells us a good chunk about the system. Now, why we care about it now is because, remember, our goal is to hit the following poles of S is equal to -2, -3, and -4. Now, we can actually expand that and know that the denominator that we want to have would be S plus 2, S plus 3, and S plus 4. Now, if we distribute that, I know this seems a little weird and you might not fully follow why I'm doing what I'm doing, but just keep looking. We distribute that and we're going to get the following polynomial: S cubed plus 9S squared plus 26S plus 24. This is our desired, our goal characteristic equation. Now, why do we care about that? Because realize we just found the values of each. We just found Ki. We just found Kp. We just found Kb. We found each of them. Okay. We are able to match them to our desired characteristic equation. So what we can say now is, let's make some space. What we can say now is the following. We can say that in order to achieve the goals that we want, we need a proportional gain of 26, an integral gain of 24, and a derivative gain of 9. All right. And we can actually use that to define the transfer function of our PID as follows. We'll have G of PID of S is equal to 26 plus 24 over S plus 9 times S. And that's how you design a PID controller. In other words, that's how you determine the values for your proportional, integral, and derivative gains, respectively, whenever you want to hit specific goals. That's how I'll be handling this semester. This is just the tip of the iceberg of what we can do with this, how we can implement and design and approach PID controllers. But I kind of wanted to cut you guys a little break. Is there any question of this example? Any question of the math I just did? Anything you guys were able to follow? Anything that didn't make sense? I have 2 more examples that I go over. But before that, actually, I have 1 more example to go over. But before that, again, I just want to make sure. Does anyone have any questions about literally anything? All right. So let's go to our next example. Now, remember how I told you guys that we don't need to use all 3 at the same time? We can just set the gain to 0 for one of them and just not use one of the paths. This is that same idea. So in this case, I'm going to tell you, design a PID controller to give closed loop poles, in other words, your feedback poles, at -3 and -4. In terms of your block diagram, again, it's not going to change. It's going to be the same thing with just 1 minor alteration. All right, this time we're not going to be making a PID controller. It'll just be a PI controller, proportional and integral. So the output of our adder, our summing junction, is going to be our error, and that's going to go to our PI controller. This is the only change compared to the previous block diagram that we saw. Because now instead of a PID controller, we only have PI. Right, then we just add the feedback path. Now for this problem, our plant G of S, so transfer function of a plant, is going to be 1 over S plus 2. So, where do we start? First, let's just determine the transfer function that is going to correspond to our proportional integral controller. It'll just be Kp plus Ki over S. Again, notice that there is no term for KD because effectively KD is just 0 times S, which is all 0, so we don't care, right? It's off. Now we'll again compensate for that S in the denominator, and then just make a KP times S plus KI. Now, one thing I want to point out is in the previous example and this example, I had to compensate for the S in the denominator of the integral path, right? If I had a PD controller, let me just show you guys something. If I had a proportional derivative controller, then all I would need to give is just Kp plus Kd times S. I don't need to do this. Why? Because the whole reason I'm doing this right here is because of the S in the denominator, and I want all terms to have a common denominator. However, in a proportional derivative controller, both of these terms have a common denominator already. They're already over 1. So in this case, I wouldn't need to perform that extra step. That makes sense? Anyone have any question? Anyone are able to follow? I just want to clarify that it's an extra step that we need to make just to have a common denominator. All right. So what's our next step, right? Next step is our open loop transfer function. That will be g of pi of s times g of s. It is going to give you what we just made, our transfer function for a proportional integral controller, kp times s plus ki all over s times our transfer function of our plant, which is 1 over s plus 2. It was provided to us. This is just going to be equal to our proportional gain times s plus our integral gain all over s times s plus 2. Now, next step is to find the closed loop transfer function, T of s. In other words, we'll add feedback now, or actually factoring in our feedback. We'll have on top Kp, our proportional gain times s, plus Ki, our integral gain, divided by s squared plus 2s plus Kp times s plus Ki. Now, if you notice, there's 2 terms with s. There's 2 times s plus Kp times s. Now, what we're going to do is just factor it out. So the numerator is the exact same. We have s squared, but now we have s times 2 plus Kp. This will matter in a moment that we did this, and you'll see why. Plus Ki. Now, our desired poles are at -3 and -4, which again, we can figure out what our goal. Oh, by the way, this is your characteristic polynomial, or at least your characteristic equation. The polynomial, not technical. But s plus 3 times s plus 4, you distribute that, it'll give you s squared plus 7s plus 12. Now, Notice that now 7 constitutes not only for KP, but also for this whole thing, right? Whereas 12 is just KI. We have our integral value. So to show what I just said, we're going to have that 2 plus KP is equal to 7. And that's going to give you that KP is going to be equal to 5. We have KI equal to 12. And that's our results. We're going to use that to find our PID controller's transfer function. Sorry, our PI, our proportional integral controller's transfer function. This is going to be 5 plus 12 over S. When I'm doing this step at the very end, all I'm doing is plugging in the numbers that we found to this right here. All right. Any questions, comments, concerns, doubts, lack of understanding of the examples we've gone over? Your homework, this is going to consist of this. And when I put it on the final, this is what it'll consist of. Next week, we'll look at PID controllers again. But for now, this is all you got to worry about. Oh, wow. Has my audio been bad this whole class?
No.
No, it's been good.
It's fine. I think it's all right.
I have like a proper microphone on my desk. It should be better now, right? The audio should sound nicer. That's it.
Oh, that is so much better.
Sounds like
Yes.
you have like a gate on it.
So I
No.
have a proper microphone, and the whole class accidentally has been using the microphone on my PS5 controller. I only now realize. Yeah. Anyways, that's neither here nor there. Any questions about this? It's on the floor too. All right.
No questions.
So, something you should hopefully be wondering is, whoops, when to use each. All right. So we'll have our use and we'll have our we'll have our when right here. So P I D. So we use the proportional path when our system is slow, or the output response, or not the output. Yeah, the output response of our system is slow, or not reacting enough. Because remember, what the proportional does is it's going to take that error and it's just going to shoot it straight up. Especially if you have a large gain for your proportional gain, then you're really going to see that present in your output. However, there's one thing to notice, there's one thing to care about. If you use the proportional gain alone, right? P alone, it is going to leave some steady state error. Now your integral path, you're going to use it when your system gets close to your desired results, to your input, but it doesn't quite reach, right? In other words, when you have a steady state error. So in other words, again, your output settles above your steady state is either above or below your desired results. But here's the thing. Integral gain alone can be slow and it can cause you to overshoot. Now, your derivative path, it is going to reduce your aggressive movements that you make in order to hit your desired results. However, as I said before, derivative path alone does nothing. If your error doesn't change. So if your error stays constant, then this is going to be the same. Because remember, as we agreed upon earlier, the derivative of a number is just 0. Okay? Any questions about this idea? All right. Final thing, all right? Just to reiterate one last time. P, faster response. Your integral path is going to remove your steady state error. And your derivative path, it is going to reduce or remove your percentage overshoot, and it adds damping. Which remember, what does damping do? It reduces your oscillations. All right. Mathematically going too deep into the PID controllers isn't what you guys are really here for. What you really need to take away from today's lecture is what each of them do, why they matter, why you want to use one, what using one is going to add, but what it's also going to take away, how it's going to hit your system. All right, that's your main takeaway from today. That's why we don't focus so closely on the math. We did a little bit of math, sure, whatever. But the main thing of today's lecture was concepts. It's conceptually what a PID controller is, what it does. All right. Now, are there any questions about literally anything I've said at all throughout today's class?
I don't have any questions right now. I'm still processing, but
If not, then have a good night, guys. Be safe, take care, make smart decisions, focus on your job search and internship search, all right?
You too,
Um,
Professor.
if anyone has any questions, anything they wish to go over,
Is
you're free to stick around. If
okay,
not, office hours tomorrow, 11 to 12. If you can't make
Professor,
it, shoot me an email. We'll meet up. Yes, Collins.
is next class going to be online as well?
I have not determined as of yet.
Because you
I have a little falcon that flies into my room, looks into my eyes, stares deep into my soul, and tells me, have tomorrow's class online. And I gotta do what the falcon tells me.
Okay.
I'm
So
messing with
you
you.
usually do say at the end of the class.
Yes. In all honesty, I just don't know.
Okay, thank you.
Yeah. I will send out an announcement either. I'll always try to send an announcement the day before, but definitely the day of, a few hours before, so you have time to plan accordingly. You will always know.
Thank you.
Yeah.